welcome to Module 12 on evaluation metrics for regression and classification. So we've talked a lot in this course so far about losses and empirical risks and so on, the sort of measures that we were taking during training to just make sure that the model is getting better and better fit on some available training data. However, obviously, in real life, decisions tend to be made on whether or not a model can be deployed on new data that it hasn't seen in training data. And in order to evaluate these kinds of deployment questions, we need a different set of evaluation metrics to be applied on some data that we've not previously used in model development. So today we're going to talk a little bit about how choosing the wrong metric, or choosing like the easy standard metric like accuracy, can occasionally make a bad model look good, and potentially vice versa. And we're going to wrap up by just talking about this again, but it's important when we're deploying models in high-risk settings, high-stakes settings, or even in settings generally, that how we evaluate and talk about the performance of a model is correct and accurate, and if we're using the wrong metric choice, the wrong evaluation measure to describe the model, then in some sense we're not giving a true account of the performance of that model, and then therefore we're putting something out in the world in a way that is essentially somewhat unethical. Speaking of unethical, we're going to talk a few times today about fraud detection, and we'll give examples like this one. Even if you have like a fraud detector looking at some data and flagging instances of fraud, that's 99.5% accurate. That sounds great. Like very rarely do we see machine learning models achieve this sort of metric on accuracy. We can still say that even this might still miss most instances of fraud. By the end of today, you should be able to define and compute core metrics for regression. We've already talked about MSE and MAE and RMSE. R squared, we're probably going to push off to another module. We'll talk a little bit about classification metrics. So accuracy, we have a kind of a somewhat of a handle on. We'll talk about precision and recall, F1, and the so-called ROC curve. We'll talk about, you'll be able to choose metrics that align with concrete decision problems and cost structures. You'll be able to diagnose failure modes. So class imbalance is a classic one. Different values of threshold choices. For example, you're using logistic regression. You need a threshold to determine whether a data point is part of class 0 or class 1, but that decision can have major consequences. We'll talk a little bit also about optimistic metrics. By the end of the module and the component Jupyter Notebook, you should be able to implement an evaluation loop in Python that's going to use NumPy and scikit-learn. That's still going to respect the train, validation, and test splits, although that specific topic will be discussed in the subsequent module. You'll also be able to justify sort of trade-offs between different stakeholders, so users, operations, regulators, and so on. So a training loss is what the optimizer sees. We've talked about square loss, logistic loss, and cross-entropy in previous modules. However, what humans see, like especially the nerdy ones like us, is going to be an evaluation metric to help us decide if the model is actually going to be useful for our use case. So mean squared error, mean absolute error, accuracy, precision, and so on. These are all things we've talked about a little bit before. And we'll talk about AUC later today. So in an ideal world, the loss that you use to train your model and the metric you use to evaluate the model, even though those are in completely separate phases, they're somewhat aligned with one another. They're both sort of measuring the same sort of thing. Obviously, like if you're doing a classification task, you have to use a classification loss, and you want to use an evaluation metric that has to do with classification, in both cases, as opposed to regression. But they can also be aligned in different ways. We'll see one example as an aside later on today that is very task-specific. In practice, normally we train with one and report another one. One of the pitfalls that some amateur machine learning enthusiasts fall into is that they hyperfixate on the training phase, and they watch as the model sort of learns the parameters, maybe goes down into one of those wells that we talked about earlier, and kind of optimizing the parameters as it does so, and then the enthusiast will kind of report that as the performance. This is the result. The model has learned something. The loss on training data has gone down. But that isn't really a measure of how well this model is going to generalize. It just demonstrates that the parameters were updated effectively, right? But effectively to what end is not really answered by that sort of analysis. So just to make it absolutely clear, this evaluation metric is a function. Here we're calling it big M, which compares y hat and y, that maps predicted outputs, here y hat, and true labels y, to some scalar score. So the output of this function is just a number that we're going to use to compare models on some held out data set. So here's an example of things going wrong that I kind of hinted at earlier. We want to build a model that can detect fraudulent transactions. Okay, and like fraud is a huge problem, but say in a database, like a financial database of credit card transactions, fraud is still in the minority of those kinds of transactions. Let's estimate for the time being that about 1% of transactions being made in a bank's or a credit card's company's database of transactions are fraudulent. Now we have this model, call it model A, that doesn't learn anything. The only thing it does is predict not fraud for every transaction. Right? Maybe whoever designed model A looked at the proportions of fraud versus not fraud in this data set. They determined that, well, 99% of the time there's not fraud, so I can do pretty well by just assuming that it's not fraud. We call that the prior probability. So the prior probability, without looking at any other sort of variable, is that the class is 99% not fraud. So we have maybe a massive amount of training data that we could have learned a model on, but we didn't. We just have this kind of naive output. Now imagine we have a test set of 10,000 transactions, and the rates of fraud in this test set, which we haven't seen before, the rates of fraud are about the same, about 1%. So 1% of 10,000 is 100. So fine. The same model that we could have trained but didn't before, that's always going to return not fraud. We'll keep on doing so. And then on this data set, on this test set of 10,000 transactions, 9,900 instances will be not fraud, and those will be correctly classified as not fraud, and therefore the proportion of all of the correct identifications by the total number of instances in this test set is 99%. And if all we're saying is this model is 99% accurate, like it seems kind of intuitively good, like that's a very high mark in a class, so we kind of associate it with a good score. So like it's fine, but that's extremely naive, right? So as you've already guessed, if the model only predicts not fraud for every transaction, then whenever there's an instance where there is fraud, the model just will never identify it as such, because it just never outputs fraud as a possible class. So in all of these 100 instances of fraud, the model just won't recall them. We'll define recall in greater detail in a moment, but it won't find those instances of fraud, right? Like absolutely none of them will be caught. So the impact is that the model will catch no fraud while looking great by accuracy. So imagine now you're working at a credit card company, and this startup, like an AI startup, comes to you and says, we have a fraud detector that's 99% accurate. The best human is only 97% accurate, and we'll offer you our model like at a discount and so on. It seems too good to be true, and it is. Like you didn't do any evaluation, and you didn't kind of scratch the surface to detect this sort of like pathological behavior. So the lesson here in this anti-example is that a metric can be wrong, can be the wrong choice. In this case, accuracy is the wrong choice. If optimizing for it, like if just trying to build towards accuracy in this case, leads to bad decisions for the real world stakeholders that we're trying to help. So that's classification. Just a reminder of regression. I talked about squared versus absolute error. We have y is a real valued number. This is the true value, and y hat is the prediction, like we talked about a moment ago. So squared error is just the squared difference between these two values. And then the mean squared error is just the average of these squared differences. So we talked about this earlier. So you just sum over all of the instances n. You compute the square difference, and then you divide by n to give you the average. This is the mean squared error, or MSE. The mean absolute error follows more or less the same kind of form, except instead of taking the squared difference between these two quantities, the true output and the prediction, we just take the absolute difference between them, right? We're trying to get rid of negatives here. And again, you just sum over all of them, divide by n to get the mean value, the mean absolute error. So, the intuition is that the mean squared error can penalize very large errors more heavily, quadratically so. And quadratic basically just means that you're doing a polynomial of degree 2. Mean absolute error, however, treats all errors linearly. Like there's no squared or cubed and so on over here. So what effect does this actually have when we're evaluating these models in practice? Well, let's take this kind of toy example. We have two instances in our test set, and the two instances, like the two predictions we want to make, the two correct ones, are 10 and 10. Right, so like data point 1, data point 2, the outputs in both instances are just 10. So the model A is a better model in this case. It predicts a little bit more close to the truth. It gets 9 and 11. And model B, which is way off here, in those two instances it'll predict 0 and 20. So what effect does this have on the metrics we chose to look at, MSE and MAE? Well, you can satisfy yourself by just computing these differences yourself, but because a model A makes a error of just 1 point for each of these two data points, one is underestimating, one's overestimating. These differences are squared, so it's 1 squared is 1, minus 1 squared is 1. You sum over those square differences, you get 2. You divide by the fact that we have two instances, n equals 2, and you get a mean squared error of 1. Similarly, the absolute differences here are also just 1 in each case, and everything else computes the same way. Your mean absolute error is also 1. But now look at this wonky model B over here. For the first data point, where the true output is 10 and model B predicts 0. Well, the absolute difference here is 10, and the square difference of 10 is 100. Okay, and similarly for the second data point, the absolute difference is 10, the square difference is 100. So the two squared errors are both 100. We add those two together, you get 200, divide by 2 because there's two instances in the test set, and you get a mean squared error of 100. And if you go ahead and do the same thing and then just plug in these values of y hat here down here for the absolute error, compare it to the true values, you get differences of 10. The average absolute error here is just 10, and you can see now there's a bit of a difference emerging between the mean absolute error and the mean squared error. So in the case where the model is fairly correct, like in model A, the mean squared error and the mean absolute error are both very small. The model makes small errors, and both of these metrics give sort of small measures of error. In the second case, where the model B makes these massive errors in judgment, mean squared error kind of overemphasizes those massive differences. So whereas a difference between these two models in mean absolute error is only 9, the difference in mean squared error is 99. Okay, mean squared error really emphasizes big differences between models, and mean absolute error doesn't. So we can compare two models predicting this daily energy demand over 30 days. as usual, here's the code, and as usual, I advise you to go ahead and copy it into a kind of temporary Jupyter notebook and go ahead and run it. So the demand, like here we're kind of, designing things ourselves just for the example. So here we have an actual true demand, and we've modeled it as a sine wave. You've probably seen energy demand. Energy demand rises during the day and it falls during the night when everyone's asleep in a kind of a sine wave sort of pattern, which we have over here. And then we have a couple of other parameters over here that describe the shape of this change over time. So the first model will, in this case, be however it's computed, whatever the architecture is, its predictions are going to be fairly close to the true demand, except there'll be this small amount of noise and a little bias of 2 over here. So it's slightly biased, but it's fairly smooth in terms of the shape of the, it follows the truth fairly well. Model 2, down here on line 14, it follows the true demand, and it also has essentially the same sort of error, which we define by this normal distribution over here. There's a little bit of noise added to its predictions, but now we've also just for the sake of argument, again, this is not a realistic form of machine learning here. We're just building it for the example. We add outliers. So occasionally Model 2 makes some very wrong mistakes, which we call outliers, which are accounted for here in line 15. And then we just go into the vector describing all of these predictions, and for a few of them that we've identified as the instances where outliers occur, we add a lot more noise. So instead of adding noise with 0 mean and 3 standard deviations, we add a noise of a mean of 30 and 5 standard deviations. And we put everything into a nice data frame and then just show its head as we normally do, and here it is. Okay, so here's our days, here's the true demand, it rises and falls. Here's Model 1, which follows it pretty closely, and here's Model 2, which has occasionally large errors. You can see some of that emerging here already. So on day 1, the true demand is about 104, and both models 1 and 2 are within 3 or 4 points of that true demand. Line 2 is also similarly very close. Both models 1 and 2 approximate the true demand fairly well. But then we get down to day 4, and then we have Model 1 still doing a fairly good job of tracking the true demand. But then this is one of the outliers previously mentioned for Model 2. Now Model 2 is off by a factor of 30 absolute. So there's a couple of measures we can compute here. So from sklearn metrics, we can import mean squared error, mean absolute error, and R2 score, which we'll talk about a bit later. R2 score is essentially a measure of how well a model fits available data. So this is nothing more for you to do really than just to call this function. So we have models 1 and 2. We have a little list over here that describes mean squared error, another one that describes MAE. And we have a mean squared error for Model 1, a mean squared error for Model 2, and we're just comparing the true demand in our data set against the predictions made by each of these two models here. And then we're just storing their mean squared errors in this list. Okay, so here the point is we're just computing these measures using the built-in APIs from sklearn, which is this fundamental library in machine learning. Here it is. So down here I just kind of printed out in line 18. So we get these values. And you can see, Model 1 being the model that's a bit more accurate. Model 2 is the model with these occasional outlier fluctuations. Both of these models have mean absolute errors that are both fairly low. Model 2 is worse, it's true, but mean squared error, again, mean squared error overemphasizes these big differences. It will assign much more of a penalty essentially to Model 2 than to Model 1, and you can see just factually from the data we've produced, the mean squared error is about 10 times higher for Model 2 than it is for Model 1. Now just, it's always a good idea to do it yourself. So we're just going to compare the metrics we just obtained from sklearn. We're also going to compute them ourselves. I want to emphasize how simple this is. So, I mean, you can see in your mind how you might write a little function to compute the mean squared error. You have a for loop that iterates over instances in a list of test cases, computing squared errors as you go, and you sum them up, and then at the end of that loop, you just divide over the total length of the vector. So you can do that in sort of a loop, but you can also do that in an easier way. So you can do that in a vectorized way. So here we have the vector true demand, which is just a vector of all the true demands, like our true data y. We have all of our predictions made by one of our models, in this case, the model 1. You can take those two vectors, subtract one from the other. These are just the absolute differences. So that's kind of the inner loop when we're computing all these differences between one quantity and the other. We've turned that into a vector operation of one vector minus another, obtaining a vector of the absolute differences. On line 3, we just take the squares of all those errors. So instead of having to loop over every element of this vector, errors star 2, which means errors to the power of 2, or errors squared, computes the squared differences now. And then the mean of anything, by default, is just the sum over all of the elements divided by its length, and then we can get that in one shot by just calling the mean function from NumPy. And the same sort of logic applies to line 4, where we're taking absolute differences instead of square differences. Now, just for sanity, it's always a good idea to double check things, even if the outcome might seem obvious. We compare the mean squared error and the mean absolute error computed by sklearn a moment ago with the values we obtained manually just for our own second checking to make sure nothing funky is going on. Like either we're funky things that go on could be that we're calling sklearn in a way that is incorrect in some way. So the values we're getting from sklearn are not correct, and but the ones we compute ourselves are. So that difference might drop out of this kind of analysis. On the other hand, maybe we are calling sklearn correctly somehow, maybe by accident, but maybe our understanding of what mean squared error and mean absolute error are incorrect. So, we want to implement that ourselves just to make sure that we conceive of these concepts, simple as they are, correctly. So we go ahead and go this exercise. We try to, we do lines 3 and 4. If some difference occurs between the manual computations of these quantities and the ones that sklearn provides for us, that might be an indication that we actually don't understand what's going on too well, and that would also, require some follow-up. But as you've probably already seen here, there's no difference. The values between sklearn's computation of mean squared error and mean absolute error and our manual ones are exactly the same. Everything seems good, and we can go ahead and proceed. Just for visualization, you don't always have to do this, but I just wanted to visualize what we just sort of looked at. This graph just basically graphs over all of the days, the true demand in blue, more or less periodic, against the Model 1's prediction, which is fairly close, but with a little bit of jitter, a little bit of noise, and Model 2 in green, which is sometimes pretty close, but occasionally, especially in the early days, has a massive amount of error in terms of these few outliers. So, Model 2, in some sense, might have similar average error, but these huge spikes are problematic and might need to be dealt with in some way. If these large spikes are actually catastrophic, then this mean absolute error, or even this max error metric, may be I say more relevant than MSE. So the classification, back to classification now, and the confusion matrix. The confusion matrix is essentially a two-dimensional table that compares possible values of classes against each other. On the one dimension across the rows, we have the true values, the actual labels that we're trying to predict, and then across the columns we have the labels that are predicted by a model that we're looking at currently. Now, occasionally these things are swapped, so occasionally this table is pivoted, and then the predictions occur along the rows, and then the actual values occur across the columns. I mean, if that's the case, or in any case, it should always be made obvious. So in this little table over here, we have like labels. This is the actual, instances of fraud, not fraud, and predicted values are the columns that normally should be applied, like should be given to you. Regardless, this upper left-hand corner will always be the true positives, regardless of whether or not you have to do this pivot or not. So what this element over here basically is saying is this is the number of instances in our test set in which these are actually instances of fraud. So these are positive cases of fraud, and the model has correctly identified these instances as being instances of fraud. So in other words, this is a true positive. It's been classified as a positive, and it truly is a positive. That's where the name comes from. Down here in the bottom right, these are all instances where actually there was no fraud in these credit card transactions, and the model correctly identified that these were not instances of fraud. So in other words, the model thinks that these are negatives, and they truly are negatives. So these are true negatives. This is correct. These are correct predictions, and we're generally happy. Now we go off the diagonal. So up here in the upper right-hand corner, we have, actual instances of fraud. So these are cases, credit card transactions where fraud occurred. The model predicted not fraud. Okay, so what did the model predict? The model predicted negative, said no instance of fraud, but this was false. Okay, so it's a false negative, or FN. And then down here, finally, in the lower left-hand corner, we have actual fraud cases predicted as fraud. So the model says positive, but this is false, so it's a false positive. And we're done, right? So in real life, we're gonna have this table. We'll have numbers in each of these elements of the table. So we'll just count up the number of instances in which the model says fraud, but this is not fraud. There'll be a number here replacing a false positive FP. I'd recommend that you might want to write this down yourself a few times. There's many ways that you can learn a new idea. And if a confusion matrix is a new idea for you right now, it won't take too long for you to just take some paper and then just write it out a few times until you kind of get what's happening here, right? So maybe try to write it from scratch without looking at the screen, and then come back to the screen or these slides, and then just see if your understanding of how these four quantities are arranged across the confusion matrix is correct. And if not, then iterate and try to identify what kind of trouble you might be having. I think a good mnemonic to try to remember as you're going through this exercise of trying to remember what a confusion matrix is the second word in each of these quantities is the label assigned by the model, right? So the model is the thing saying that these are positives, right? Or negatives. As you can see, you go down the column. The prediction is fraud. This is a positive instance of fraud. Every element in this column is positive. On the other column, this is a negative instance of fraud. There's no fraud. Every element of this column is negative. Okay? And then the true or falsity of this is measured against the truth of reality. So if a model says something is positive and it's true. If it says something is positive and it's not actually positive in real life, and that's false. All right? It's an error. And that's a fairly easy way to just remember what each of these quantities refers to. Now, this confusion matrix is sort of almost like the intermediate step between the outputs of a model and the actual measures that we want to convey in our reports or to our colleagues or to the real world and so on. So we've kind of talked about accuracy at a very high level, and we just kind of ignored how it's computed under the hood. Accuracy can be computed in a couple of different ways. So technically, you can just go through all of the instances of all of the outputs of your model, and then just check whether or not the label matches, the predicted label matches the true label, and then just count the proportion of those instances, and you get your accuracy. You can go a little bit deeper, and you can measure instances where the labels match because it was a true instance that was classified as true, or positive and was classified as positive, or it was a negative instance classified as negative. Accuracy is basically just the sum of these correct classifications, which is just the sum of these elements down the diagonal of the confusion matrix, divided by all of the instances across the entire table. So it's the true positives plus the true negatives divided by, well, the true positives plus the true negatives plus the false positives plus the false negatives. Okay, like it's like this confusion matrix will have, like, every instance will have to be one of these four instances, at least for binary classifications like this one, where there's predictions of fraud and not fraud. So precision basically asks, well, in all of the instances where our model said something was positive, what proportion of those instances was actually positive, was truly positive? So here we care about true positives, but we're normalizing that against all of the instances of the model saying something was positive. Well, when can a model say something was positive? It can say so in the case where it actually was positive, in which case those are true positives, or a model can say an instance is positive and get that wrong. Those are false positives, and those are the only two real examples. So precision is just true positive divided by true positive plus false positive. So I think we've described that pretty well. Recall is a subtly different measure. What recall is asking is, of all of the positive instances in the actual test set, what proportion of those real instances of positive were captured or caught or recalled by our model? Well, our model only caught the ones that were true positives. So that's the proportion, that's the number of true positives, divided by the number of instances that it correctly caught, the true positives, plus all of the instances of positives that the model incorrectly classified as negative. So in other words, the false negatives. So a false negative was classified as negative, but it actually was positive. Okay? So this proportion is recall. We talked about this kind of difference a little bit in previous modules. In some instances, you want to maximize precision. You don't want to make a ton of accusations of fraud, in which only a small number of them actually turn out to be fraud. There's all these costs associated with that kind of accusation, so you want precision to be as high as possible, right? On the other hand, you also want to catch every instance of fraud out there, right? So you want to, in some sense, have a very low threshold and be a little bit paranoid about it and try to just capture as many instances of fraud as possible, so none of those instances of illegality fall through the cracks. So precision and recall are a bit at odds with each other, right? So precision is basically telling us to be as discriminating and careful as possible and as confident as possible, and to try to basically minimize the number of false positives you're making, right? So you don't want to accuse someone of having committed fraud when they didn't. Be very cautious. Recall is almost asking you to do the opposite. It's saying, I want to minimize the number of false negatives. I do not want to say something is not fraud when it could be, so I want this number to be as small as possible. So I'm be happy to make some false positives if all you care about is recall, as long as false negatives is minimized. So sometimes in the real world, the decision between focusing on precision or focusing on recall is an obvious one, and you can go ahead and choose one or the other. But in many instances, especially in instances where the costs are similar between false negatives and false positives, you can just combine these two quantities together. So for now, we're just going to leave this here as the definition of F1 score. This is a harmonic mean. It's just precision times recall divided by precision plus recall multiplied by 2. This is one of those scores that you'll probably learn best by just trying to write it out a few times and eventually kind of identifying which operation goes on the top and which goes on the bottom, multiplication or addition. But just writing it out a few times in your notebook periodically will help you just memorize this score. We'll come back to this in a future module. So here's just a visualization of what I just mentioned, and maybe a bit more of an intuition. You can read more about it at this link down here. This graph, I think, is a nice visual way of thinking about what we just talked about. So this circle represents all of the instances of like positive classifications by our model. In this case, it's described as retrieved elements. So out of all of the transactions that occurred, these are the ones that were retrieved for analysis. These are the ones that were flagged as potential fraud. We'll see a bit later instance like a task of recommendation systems, like a search engine online, and recall and precision tend to also often be used in instances where we're trying to figure out which web pages to return to a user given a query. Regardless, for now, these circles represent all of our positive classifications. Now over here, this column over here, identified as relevant elements, these are all of the elements which are truly, in this case, fraud. Okay, so out of all the elements that were fraud, some of them were captured. These are the true positives. Some of them were not classified as positive. These are the false negatives. These are the ones that were classified as negatives, but this is false. These should have been classified as positive. And then we have our recall down here. So you see visually, recall is just the total number of instances we correctly classified as true divided by the total number of actually true cases. Right? So we kind of captured or recalled this proportion of all of the ones we should have. We want this circle, in some sense, to be as green as possible. We want to make as few errors as possible. If we return a handful of items as potentially fraud or flagged as fraud, we don't want to waste anyone's time kind of tracking down instances that turned out to be flagged in error. So it's just the proportion of all of the over all of the instances flagged as fraud, what proportion of them were actually fraud, which proportion of them were actually true positives. So again, make sure that you understand this intuition. Precision is just identifying the proportion of times that you are correct when you flag something, and recall is how well you are at gathering all of the instances of a positive case, in this case, true frauds. Okay. Again, this is relatively simple, but make sure you understand this distinction. So staying with this idea of fraud detection, we're going to simulate 2,000 credit card transactions, and now this is a bad neighborhood. So instead of 1% fraud, maybe we have 5% fraud. So here's just some code that we use to do so. Nothing much is happening here. We have our random seed just to keep things reproducible. Here are 2,000 instances. We have a log normal distribution with means and sigma set. We have a little bit of extra features. So just like a data set will have a couple of different measurements for us. We're measuring whether or not this credit card transaction took place outside of somebody's normal country of residence, whether this other country was flagged as being a high-risk country, like some countries might have more instances of fraud than others, and so on. Right? We also measure when the credit card transaction took place, and whether or not this device was trustworthy. Right? So if you have like an unpatched mobile operating system, then maybe this is not a trustworthy device. If you're using like Graphene OS or one of these like hardcore security OSs, maybe this could be flagged as a trustworthy device. This is all fictional. So here we just have a like logit. So logit, this is our kind of data generating value that basically just combines all of our input features, whether or not something's international, whether or not it's from a high-risk country, and so on, and computes everything together into an overall probability of fraud occurring, which is logit p, and then we put logit p into this function on line 20, which you'll recognize as the sigmoid function. Now we have a binomial distribution that basically just flags, given this quantity p, this probability, we compute the binomial distribution from p, And then this gives us the fraud rate. So this is just sort of a sanity check at the bottom here. So what is the fraud rate? Well, given all of these numbers we put in here, we've managed to get a fraud rate of about 5%. One other thing I want to flag quickly is that, again, these slides are essentially Jupyter notebooks themselves. So, every slide is sort of like or every code block is a cell in a Jupyter notebook, essentially. So currently on slide 11, I've imported from sklearn metrics, which is the topic of today's module, a relatively large handful of different functions here. Accuracy score, precision score, we saw these a moment ago. So I'm not using that yet on this slide, obviously, but I'm going to use them in subsequent subsequent slides. Okay, so let's take a quick peek at the data. I'm just putting all of the variables we just computed previously, naming them with labels, putting them into a data frame, calling that data, and then showing the head. So here are the amounts of the transactions, whether they occurred internationally, and so on, all of the variables we just talked about a moment ago. So at the top of this data set, there's no instances of fraud. Indeed, fraud is very, very uncommon. If we split the data and always choose not fraud, remember we had the pathological kind of pretend model where whoever designed the model said, well, in that case it was 99% of the time, now it's 95% of the time approximately, but 95% of the time it's not fraud. If I just classify not fraud all of the time, regardless of the hour and the trustworthiness of the device and where the transaction was made and so on, I'm going to seem to have a 95% accuracy, and everyone will love me. So if you were to do that and compare, this is left as an exercise to you. What is the baseline accuracy? Well, the baseline accuracy on some test set is going to be like approximately 95%. And the recall, as we saw earlier in our hypothetical example, will be 0. All the instances of fraud will never be caught by a model that always outputs not fraud as its class. So, I mean, that's kind of a pathological bad example. It's a bad baseline. What does an actual training look like? We can go ahead and take our logistic regression model that we talked about in a previous module, and actually train something. So here's logistic regression, which I imported in a previous cell from sklearn. This is going to help us, actually learn the regression and fit. So a lot of classifiers and regressors in sklearn have this built-in function fit, which just takes a bunch of training data. In this case, input training data X and output training data Y. And however it does it fits these two quantities to each other. When I say however it does it, what I mean is that like a logistic regression will fit its parameters in one way, a neural network will fit them in another way, and so on. But this is all kind of hidden to you by this one command fit. Okay, so now we have a model that's been actually trained on the data that we obtained. It actually cares somewhat about the hour of the day, the trustworthiness of the device, the international nature of the transaction, and so on. So remember, one of the reasons why we wanted to use logistic regression in the first place, compared to a couple of other models, is that it gives you roughly a probability or a probability estimate of the likelihood of a positive outcome or not. So this logistic regression has a built-in function predict_proba, which basically just takes in this case, the test data, so X test, and it will return just the individual probabilities of the positive instance. What is the probability of a fraud in this case? Okay. Now, all you have now is a big vector of probabilities, Y proba, and I have this threshold that says, well, if the probability is 50% or above, classify it as fraud, and otherwise classify it as not fraud. So here I compare all of this vector of probabilities against this particular number. This comparison will give me a Boolean value, true or false. I can cast that value, true or false, as an integer. So if it's true, I get a 1. If it's false, I get a 0, and I store all of those quantities into this new vector, y_pred. Okay. So I have y-test, and one of the reasons why I do this is because y-test is also just a vector of binary numbers, ones and zeros for positive cases of fraud and negative instances of fraud. And I mentioned a moment ago, all of these metrics that I'm pulling out of sklearn are now going to be called here. So I'm just comparing y-test against y-prediction. I get my accuracy, my precision, my recall, and so on. Okay, and then I'm just printing them out. So to some extent, unfortunately, this logistic regression model kind of falls into the trap that we've laid for it. It also, just like the pathological model, will give an accuracy that is very high, right? Like 94.8% seems like a very high number. It's an A+, right? So it should be good. But the precision we get for fraud and the recall we get for fraud are all zero, which is obviously not what we would hope to have in a model. I want to mention for a moment, this is something that's a bit kind of too deep for the moment, but I'll mention it anyway. Occasionally when you get scores or any kind of fractions, you can run into the instance where you can have divisions by zero. So if you happen to have, you know, a proportion of true positives and false negatives that I guess would be recall, that are both zero, then you know, division by zero is unhandled. You might have a exception that would break the flow of your script. This parameter here just tells you what to do in the instance where you're dividing by zero. It says just return zero. So whether or not these are actually zeros or whether these are the results of divisions by zero is up to you to decide when you look into the code yourself. So anyway, we had the pathological silly case of always returning not fraud. We tried to do better by fitting a logistic regression model with our threshold 0.5, and we kind of failed to get any decent precision and recall there either. We take a peek at the confusion matrix, which is usually a good thing to do. If you're getting weird evaluations of this type, you want to open up your confusion matrix and look at how the numbers are distributed. As we've mentioned a moment ago, you generally want to have high values along the diagonal. These refer to true positives and true negatives. Here they're kind of flipped. So here are the positive cases on the bottom. Previously it was on the top, but you know, everything's labeled appropriately, so you can find out where the true positives, true negatives, and so on are. So very quickly here you can see, well, the vast majority of all of the instances in my test set are truly not fraud and are classified as not fraud. But I have 0 instances of fraud labeled as fraud, and I have 0 instances of not fraud labeled as fraud. So in some sense, even though I've trained the model, this logistic regression model, to fit the data and give me good estimates of fraud or not fraud, it also fell into the trap of only ever predicting not fraud. Like 100% of all of the decisions are in this column over here. The predicted label is always not fraud. So again, if all you're doing is talking about accuracy, which is like one of the most like noob-ish ways that you can approach evaluating machine learning models, you can have really high accuracy. You might even, like if you're really amateurish, you might try to show off about how high accuracy you are, but then as soon as someone who like knows anything about anything will ask you to scratch the surface a little bit, they ask to see your confusion matrix, you'll be extraordinarily embarrassed by your lack of curiosity and understanding. So you would never do that, right? So all these examples are instances of people from other universities who are not as curious as you are. Obviously, like a recall of 0 will be too low for the fraud team. If you have a team of people waiting to get instances of potential fraud for them to look at and follow up on, and they never get anything, that's going to be very bad for the organization, the company. Now, one thing that we still haven't tried to look into really is this threshold 0.5, right? So we kind of just randomly took it as like a halfway point between 0 and 1 on the probability scale, but maybe another threshold would give us very different values. And maybe if we tried different thresholds, we could measure precision and recall and eventually get something that might be decent. So let's go ahead and try that. So the the ROC curve. The ROC curve is like the confusion matrix, is one of the visualizations of the performance of a model that we tend to see quite often in reports, of performance. So we can treat the threshold, which we previously set as 0.5, as just a simple dial. We could set it to anything we want from anywhere from 0 to 1. And whatever that setting is, right, I'll just go back a second. Where was that? Up here. So here, I set the threshold to be 0.5, and if this is true, then it's classified as true, as fraud. If it's not true, it's classified as not fraud. So I'm going to basically change this 0.5 to any of those other possible values. I want to mention right now, the reason I went back to this code is I can do that without having to do much of anything, right? So I do not need to do any inference anymore. So line 4 is where I compute the probability of fraud on my test set. And changing the value of my threshold does not require me to go back and recompute all of these probabilities again. So computing probabilities can be somewhat expensive, somewhat time-consuming, not very, but it can be, especially for massive models. But I don't need to do that. I guess I've already have y prob a saved somewhere. I don't have to do inference again. I don't have to make those probability estimates. And you certainly don't have to retrain your model, right? So you don't have to, set your threshold to 0.1 and then retrain an entire model and then reobtain all of these new probability estimates, because those won't change whatsoever as long as the random seeds are already set. All I'm doing is changing this number over here. So it's very simple, right? So a good metric should be pretty quick to compute, and this one is, at least to the extent that you're not retraining models and re-estimating your probabilities. Anyway, we can now just kind of dial the threshold back and forth. So that's what we're doing along the rows of this table. We have a threshold, it's initially 0.05, then 0.14, then 0.24, and so on. We're just kind of dialing up all the way to 90%. Okay. We call these operating points. So a threshold set to 0.5 would be an operating point of threshold 0.5. And we can compute precision and recall for each of these thresholds. So down here is more or less where we had our threshold previously, around 0.5, and our precision and recall are 0. But as you can see, with smaller values of these thresholds, I might be more likely to flag instances of fraud, and then my precision and recall suddenly have true positives to contend with, and then therefore, because true positives are the numerator of our computations for precision and recall, I can start computing something positive. So I have all of these different values for all these different thresholds. The receiver operating characteristic, or ROC curve, will plot the true positive rate, or recall, against the false positive rate, or FPR, as we sweep this threshold from very low values to, like, where almost everything is going to be predicted fraud, to very high, where almost nothing is predicted fraud, right? You have to be extremely confident that something is fraud in order to overcome a very high threshold. And here's the code to compute it. So here's our ROC curve. We have all of our Y tests. This is the true values that we're trying to predict. Here are all the probabilities that my logistic regression computed for the probability of fraud. You pass this into ROC curve, which is one of the functions we loaded in a previous cell, and then we obtain a handful of metrics. So ROC curve returns 3 variables: false positive rate, true positive rate, and the ROC thresholds. You can also compute the ROC AUC score. AUC stands for area under the curve. It's essentially like an integral underneath the curve we're about to show you in a moment. And then we'll just plot it. So we have, where is it? That we have our variables here: true, false, positive rate, true, positive rate. And then we just plot them from 0 to 1. And we're good to go. So this is what a ROC curve looks like. We have a false positive rate on the x-axis, the true positive rate or recall on the y-axis. And every point on this line curve essentially is a different setting for the threshold. It's a different where is it, operating point. And here's the curve. So what we kind of would like to see is a false positive rate to be like always as low as possible, to more or less hug this left wall. And we want a true positive rate to kind of generally be always as 100%, right? So basically hugging this top ceiling over here. So we want this blue curve to be kind of all the way up as close as possible to the upper left-hand corner. So the area under the curve is essentially just, as the name suggests, the total area under this blue curve, which we've obtained from the code already. This is 0.797. The random baseline is one that's basically like always 50-50. That's this curve over this line over here. So the ROC AUC, or the area under the ROC curve in this example, approximates the probability that a random chosen fraud gets a higher score than randomly chosen non-fraud. So like this is a random ranking, and yeah, that's essentially it. When we have very like imbalanced problems like fraud, sometimes a precision recall curve or a PR curve might be more informative. Here's a paper that sort of describes why that might be the case. This shows how much precision we have to lose in order to push recall higher, right? So remember, precision and recall can be thought of as somewhat at odds with each other. And if you lower your threshold, and you're going to accept more instances of fraud, what that means is that you're more likely to also accidentally flag false cases as being truly fraudulent, in which case precision would go down. So how much do you lose in precision when you expand the pool and increase your recall, and vice versa? This is somewhat of a pathological instance over here. As our decision threshold gets to around 50%, we'll never actually recommend or identify any possible instances of fraud. So the score goes down, like both precision and recall go down to 0, like we saw earlier. But over here at the beginning of this curve, you can kind of see a bit more of this trade-off. As you get down to very low decision thresholds, where you're more likely to flag things as fraud, recall gets relatively high. You get up to about a 70% recall rate. So you're catching a fairly good amount of the small number of frauds you have in your data set. But you're doing that at the cost of increased like false positives, which lowers precision. So precision kind of drops off as you get really high recall. As you raise your threshold and you get more discriminating and less likely to flag everything as fraud, recall will go down, but precision will go up. You'll make somewhat better decisions, and at some point they'll cross over here. So that's fine. So again, the nerdiness in us wants to measure things in terms of precision and recall, but this is all in the aid of some real-world task. In this case, we have a fraud team that consists of a few experts in fraud, and they're taking the outputs of our model and then they're doing some kind of follow-up. They're doing some like human-level interventions or human-level investigations. Maybe this team of humans can only investigate up to about 50 alerts per day. So they can't deal with an overabundance of flagged cases. So in that case, they might have like a minimum number of cases a maximum number they can see per day. And similarly, they say, well, if we miss fraud, this can cost X dollars to the company, but annoying users, we've computed somehow costs Y dollars, like because an annoyed customer will call us and will complain to us on the phone, which will cost us time and therefore money. So there's some kind of cost associated with false negatives, missing fraud, and there's costs associated with false positives, calling things frauds when they're not. It's possible that we can therefore optimize recall at fixed levels of precision or precision at k, but we'll talk about that in a future module. We'll talk a little bit more now about how these shortcuts are, how like sometimes metrics are like tell the wrong story. So one of the main things I'm trying to emphasize here is that merely trying to demonstrate that your model achieves high values on some of these scores can ignore like real world problems that the model is facing. So this is a widely told story. It may be apocryphal, it may be false. Here's a couple of links you can follow up on that describes this sort of urban legend of computer vision in the wild. So the idea here was that the US military trained a rudimentary neural network on images of tanks to basically try to identify camouflage tanks in forest photos. I've heard a couple of different instances of this story, which kind of indicates that this might be apocryphal. In these links, they talk about photos being taken on cloudy days versus on sunny days. So in the training set in this story, photos with tanks were taken on days that were cloudy, and photos without any tanks were taken on sunny days. The version I heard was that photos of, like the idea was to classify American tanks versus Russian tanks. At the time, the two countries were not friendly with each other. All of the photographs of American tanks were done on American bases with high quality film, and all of the photographs of Russian tanks were taken with spy cameras, black and white, hidden spy cameras taken from bushes. So the images were black and white, they were grainy, they were low resolution, and so on. And essentially, in both of those versions of the story, the images of the tanks, Russian tanks versus the American tanks in my version of the story, or the photos of the jungle with tanks or without tanks, gave very high performance in terms of, say, accuracy. There were some held out images. Everyone in this supposed experiment seemed to do the right thing, and they had a held out data set of images that were not used for training. They computed the measures of performance, recall, precision, accuracy on whatever data they had, and the performance looked pretty great. But then they took new photos that were not in this held out data set, from some other data set of tanks or from background images, and then suddenly the performance collapsed to essentially just random chance. Now the story goes that the network in these links would learn not, there's a tank hidden behind the trees versus there's no tank hidden behind the trees. It was far easier to just detect cloudy skies versus sunny skies. Like there was an awful lot of the image that was either gray or blue in the upper regions, and that's an easy classification to make. The weather in the background was very highly correlated with the class, right? So like 100% of the time in this example, all the photos with tanks had gray skies, and all of the photos without tanks had sunny days, right? Or in the version of the story that I heard, which I actually like better than this, all the images of Russian tanks were in black and white. All of the images of American tanks were in color. So you could do very well. A neural network could learn, just see if there's any color in this image. If there is color, classify it as an American tank. You're going to get 100% precision, 100% recall, 100% accuracy, and it'll look really good to your bosses. Now, obviously, this is sort of a pathological case where the model might look good on paper, but it's obviously attending to the wrong thing. In each of these instances of this story, you would want a model, like a computer vision model, that could detect, the barrels of a gun, maybe compare the shape of a barrel of a gun between two kinds of tanks to classify them from one nation or from another. But instead, it's looking at just the color of the sky, essentially, right? Which is not going to be very helpful in a military operation. So metrics can be very high even when the model is using the wrong features. And there are these instances of confounders. So here, weather is correlated with tanks. This can make an offline evaluation lie, right? So because the data, that was held out for evaluation came essentially from the same collected data from this story, this problem of confounds existed both in the training set and in the test set. This is an instance of, or it would be an instance of shortcut learning. This is when models latch onto easily predictive signals, but not the true concept we care about. So that may be apocryphal, but essentially the same story comes up in real life also in medical imaging. So there's dermoscopy data sets. You can click on them here and here to identify them. And they're looking for malignant lesions. So they're again taking images as input. They're using computer vision models to predict some kind of class, and in this case, the class is whether or not the lesion is malignant or not, whether or not it could turn into a form of cancer. Now, there's a problem here, which is that if a doctor, like a trained medical doctor, who understands the differences between skin lesions, can suspect that a lesion might be a cancerous growth, they will take extra steps to sort of measure its growth over time. So what they might do is they might have a photograph with a ruler next to it, or they might kind of draw some kind of circle around some kind of frame around the lesion, so that when the patient comes back, maybe in a few weeks, they can again take another measurement and then compare and then see whether or not it's growing or not. And that would basically confirm that it's cancerous. Okay, so if a lesion is not malignant, and if an expert says there's no possible way that this could potentially be malignant, they're not very likely to put the ruler next to the skin lesion to measure it. So all of a sudden, by just following normal medical practice and using their knowledge about what is potentially malignant and what isn't, these images now have extra information in them that is very highly correlated with the outcome you're trying to predict. Okay, so it's going to be much more likely that if a skin lesion is cancerous or potentially cancerous, there's going to be a ruler in it, or maybe some marker ink around it. So these are also confounding factors. So go ahead and read this paper if you so choose. This is not in the exam or anything, but this sort of describes this phenomenon. And other researchers also found that, well, if you just sort of segment out only the lesion and you ignore everything else, so in this case you're kind of cutting out where the ruler is or where the marker ink is, then a computer vision model that's trained on these images will perform much worse on these kinds of infilled or inpainted, segmented out instances on the bottom than they do on the top, which would suggest that these computer vision models are not just looking at sort of the color and the shape and the overall boundary of these lesions to make its determination of whether this is cancerous or not, but it turns into a ruler detector, right? And the neural network will automatically learn that, well, if there's a ruler there, this is a very good signal that this is cancerous, which is sort of cheating, right? We want to, it's cheating because we were using the essentially the label provided by the doctor. So there's lots of challenge images that explicitly show this ruler marker artifact as an example of problematic bias. You can read a lot more about it at this ICASP paper, and I really recommend you do so. So this is one of those instances, again, where you're doing experiments and you're computing all of these metrics. They would look very good on paper, but unfortunately, there's something else going on behind the scenes that's giving you metrics that look good. Okay, so we talked about this imbalance problem where merely classifying everything as a negative case will give you very high accuracy, but this doesn't tell the full story. And then we talked about using precision and recall as possibly a means around that. We showed that, well, precision and recall might give you more information, but it will not get around the problem of incorrectly set thresholds. We need to set the thresholds appropriately. And now we're talking about these shortcuts and these confounds. So this high ROC or AUC on a held out set won't necessarily guarantee that the model has learned anything medically meaningful. you could have really good. You could make sure that the data is not imbalanced. You can compute your precision recall. You can compute your ROC curves over a variety of thresholds, and everything might look very performant at that point, but it's performant because the model is attending to something in the data that it shouldn't have available to it. These are called confounders. These are features that are highly correlated with your label, but are not necessarily part of the causal mechanism that you care about. You want to know that this skin lesion is malignant, not because there's a ruler in it, but because of its shape and because of its other sort of characteristics. So when you're evaluating things, it's going to be important not to just satisfy yourself with the fact that your method or your model is getting high values, but you have to actually ask yourself, what is my model actually using, and not just what is my metric. So common threats to evaluation include sort of the train test contamination. So like data leakage via feature engineering, we'll talk about that a little bit later. Using the test set to tune hyperparameters, we talked about previously, and we'll talk about again in the future. Distribution shifts, evaluation on the time period and deploying in another. So training all of your data, all of your model on data from, say, the early 2010s won't necessarily help you in the mid 2020s. You're going to have new user populations, new devices, new behavior patterns that have to be accounted for. And then, of course, these confounds or these shortcuts. So a metric can look very good, but it can look very good because a model is exploiting a shortcut, like hospital ID instead of patient state and so on. There are various ways you can mitigate against these, and we'll gradually see more and more of them throughout the course. But of course, being strict about held out test sets will always be important. So having a kind of a final exam mentality. Logging your experiments and metrics, so basically storing everything and versioning them. ML Flow is something I'd advise you to look at now. We're probably going to see it throughout the course also, but ML Flow is a pretty simple library that works in Python and other languages. It models it records your models and your metrics and the parameters and the hyperparameters you're using to tune your models. And constantly evaluate on fresh data, and also constantly asking yourself, like double checking your outcomes. Right. So I mentioned earlier that some tasks just lend themselves to certain kinds of evaluations, right? And you don't necessarily want to just kind of blindly use accuracy for any variety of situation you find yourself in. So I think it's a good idea to keep an eye open for what I call bespoke metrics based on different kinds of task. And in particular, one of the tasks that I think exemplifies this well is search and recommendation. Okay, so in search and recommendation systems, you might have a query, you put it into a search bar, and then the system, the AI, will give you a ranked list of, say, documents that it thinks, so to speak, has information for you that you're looking for. And it's not, you can look at like a case by case and look at every element that's returned and check whether it's correct or not, check whether it's relevant or not, which is basically the same thing. But because recommendation systems are used in reality, like the ordering also matters, not just the proportion of correctness, but the ordering, right? So a user of a search tool online will maybe look at the first page of results, maybe increasingly the second or third, but they won't, just because 90% of what's returned on pages 1 million to 2 million are correct, like the user just probably will never get there, so they're almost kind of useless. So we want a way to look at the relevance, say on a scale. So here I'm saying that relevance goes from 0, totally irrelevant, to some high degree of relevance. But I also care about the ranking. Okay, so rank can be like the rank 1 is the best. That's the one that everyone's going to see. Rank 2 is second best. Maybe some people don't even get there because they clicked on the first link and that was satisfying to them, and so on. So the ordering also will matter. So we want highly relevant items to appear early. So the very top ranks should be mostly results with high relevance. Less relevant items, for a good search engine will push them down the list, maybe back to that millionth or 2 millionth page. And medium low relevance will not be seen as often. Users who only scan the top few results, in this case, will generally still get a good performance. So even if the user only sees 3 or 5 items, they've probably seen like the most relevant things if everything is set up correctly. So yeah, we want a way to rank quality on order, okay? So this is just one way of doing things. This is an aside, so I'm not going to ask you to memorize any of this, but nevertheless, the point of this class isn't just to help you pass a test, but it's to help you in the real world afterwards. And search systems, recommendation systems are very popular, and the way that we evaluate them come up in situations other than just search engines online. So I'm going to walk through this just so you understand how the real world works. So the first thing we want to see is, well, like what kind, like if you have a search result, a result at rank I. So you have a ranked list of results returned to you, and you want to say how good that result is, how relevant it is. Well, we call this the gain. This is the gain that you get at rank I. And this is going to be written as 2 to the power of rel I minus 1. We'll see kind of why this like is useful in a few moments. But as you can guess, you know, if you have a high relevance, rel I is relevance. So a high relevance will give you a high score, and a low relevance will give you a low score. Now, that's one aspect to it. We want pages to be relevant, but we also want to make sure that the pages that have a small I, ones that are ranked highly, will maybe be discounted less, and the ones that are further down the list, ones with a very high I that we don't care as much about, because we're never going to see them, we'll just discount the score, right? We'll scale the score down a little bit. So a extremely relevant result will have a very big gain, but we'll discount it. We'll lower its score based on how far away it is in the list. So combining these two ideas together, we have the discounted gain. That's just the gain divided by the discount. So the discount, the higher values of I will give you bigger discounts. So the bigger the discount, the bigger the denominator, which means this entire fraction gets smaller and smaller as the denominator grows. Easy enough. Now, here's where it gets a little bit potentially tricky. We have the discounted cumulative gain, or DCG. So here we want to evaluate sort of the overall system, and we want to walk down each of the returned documents in our search, and we want to compute this discounted gain for every item, and we want to kind of keep a running score of how well we're doing as we're walking down that list. And then we want to say maybe we're going to stop at a certain list. Like no one in our user group is going to read 100 pages. In fact, maybe they're only going to read the first top 10 pages. So we'll say, you know, stop accumulating these gains, these discounted gains at rank, say, 10. Okay? K, because it's a variable like this, when you're doing experiments, you could report a bunch of them. You could report DCG at 3, only looking at the top 3 values, and DCG at top 5, and DCG at top 10, and you'd report all of this in a big, massive table of results, and then you'd show like, okay, well, this model works very well at k equals 3, but it falls apart afterwards at k equals 5 or 10, and so on. So all we're doing here is, see, this is our discounted score, which we've defined above, and then we're just summing, we're just accumulating, we're adding our scores as we walk down the list. Finally, the normalized DCG is a way of comparing how well we do on our ranking, our model's ranking, against the ideal ranking. The ideal ranking is we'll have some kind of perfect system that like literally just sorts all of the pages by their relevance. So across all of our potentially billions of data points, we have the highest ranked at the top, followed by the next highest, and so on in terms of their relevance. That's the ideal ranking. I can compute DCG at k for the ideal ranking, so the values of I, like the rank I, will change in my ideal ranking. And then this proportion, like the IDCG will be the highest value possible. DCG, like any non-ideal, will be less than that, but it'll be like at most that. Anyway, this kind of gives you a proportion of how well we're doing relative to the IDCG at k, and you can read more about that at this link. So suppose we have just 5 search results, so k is equal to 5, and every search result will have a graded relevance that we somehow know. This is like a supervised signal of 0 to 3. 0, totally irrelevant, 3, maximally relevant. Here we have some fictional data of an actual ranking that like our system, how well it performs. and then we have the ideal ranking. Okay, so the actual ranking here that we get, like the first page is result A, and it has a relevance of 3. The second page is page B, it has a relevance of 0, and so on. So I'm just going to walk through this anyway, just because this might be the only time you see this. The discounted gain. So we can go back a second and look at the discounted gain. Well, the discounted gain is going to be 2 to the rel I minus 1. What is the relevance of the top page? Well, it's 3. 2 to the 3 is 8, minus 1 is 7. So the gain is 7. What is the discount? Well, the rank is 1. So we plug in 1 over here. 1 plus 1, take a moment if you need it, that's going to be 2. And the log base 2 of 2 is going to be 1, so the discount is just 1. So 7 over 1, the discounted gain is 7, and here we are. Because we're summing at every step, now the cumulative DCG so far is just 7. So the sum of 7 and nothing is 7. Just to complete this example, I'll go to the next line here, where the relevance is 0. So what is the discounted gain of the second page returned? Well, let's plug in the relevance to our gain. 2 to the power of 0 is just anything to the power of 0 is 1, minus 1 is 0, so our gain is 0. And then our discount, well, the rank now is 2. So I plug in I equals 2. 2 plus 3 is 2 plus 1, sorry, is 3. The log base 2 of 3 is whatever that happens to be. I don't really care right now. It's a positive number, and 0 over that positive number is going to be 0. So I get the discounted gain of 0. What is the cumulative gain so far? Well, previously I had 7, and I had 0 to it. Now I have 7. All right, so the cumulative DCG is 7. And after 5 instances, I end up with 10.09. So my cumulative DCG at 5 is 10.09. The ideal ranking, though, you see here, the most relevant page is ranked first. The next most relevant pages are ranked second and third, and then so on. You do the same computation on this table. The top result is the same. So the top rows is the discounted gain and the cumulative gain are the same, but then things start to change, and you can see I end up with a higher score at the bottom. My ideal cumulative DCG is 10.82, and then therefore the proportion of how well you and I do with our model that we wrote versus the ideal scenario is the ratio is approximately 0.93. Not exactly a percentage or anything like that, but it's close enough that we can call it a percentage, and then we can compare. We could run another actual ranking with another team's model and see how well we compare relative to the ideal baseline. So let me zoom out for a second. Good thing I'm not a professional YouTuber or anything, or I'd have to keep on doing this over and over again, but this is just a course, so I feel comfortable with these occasional sillinesses. So here we are. So these small metric gains. So the difference between 0.09 in our case and 10.82 in the ideal case, like this might be a small difference, and does it actually matter? So let's consider these real world systems. We have recommendation systems, in particular web search. We talked a lot about large scale fraud, abuse detection, and so on. So let's just kind of dig into a hypothetical scenario, which is nevertheless somewhat realistic. So our search engine might handle 100 million queries a day. This is not like unheard of, even with small startups in our local community. Like there's some startups that are having massive uptake like this. Okay, so we have a baseline model that we've been running on our platform. The NDCG at 10 is 0.8. And then we put some energy into improving the model. We've done an experiment, and the new NDCG at 10 is 0.81. So we got a 0.01 absolute improvement in our metrics performance, which seems kind of small. Like it sounds like 1%. It's not really 1%, but it sounds like 1%. So this could indicate to some decision makers that it's too small of a difference and it doesn't matter. And this is again the kind of naive people we have to deal with as experts in machine learning, like you're becoming. This is actually potentially meaningful, right? So suppose that an increase in 0.01 NDCG at 10 corresponds to 0.2 percentage points in click-through rates on top results. So because there's more relevant things being returned to the user up on top, at the top of the list, you're going to have more people clicking these links, and we get data, we get ad revenue, and all that sort of thing. A concept that seemed less nefarious, 5 or 10 years ago than it does today. But regardless, like it's still a metric that matters to our organization. So if we have 100 million queries a day, and we have just a small increase in 0.01 in NDCG, which results in a 0.2% increase in click-through rates, which again is seems to be within the realm of feasibility. That translates to 200,000 extra good clicks per day. Okay. Now, that means more revenue. So 200,000 clicks can mean more revenue from ads and purchases, or maybe you're gathering users to your platform and then incorporating them in your platform. And you're onboarding them. So 200,000 is suddenly like not so small a number after all. So depending on the scale you have, these small numbers can actually can result in very big absolute numbers in terms of difference. Another example is fraud. We have a model with AUC of 0.95. We have a stronger one with AUC 0.955, which again, it seems like a very small difference. But if we have a chosen operating point, like a fixed budget that we have in terms of a team that can evaluate or can follow up on flags, this can mean, on one hand, we could potentially catch hundreds more fraud cases per day, or it could mean that we're reducing false alarms by thousands per day. So a 0.005 difference reduction in false positive rate or false negative rate can still nevertheless have a lot of massive impact on your bottom line. So at scale, what appears to be a boring 0.5% gain in standard metrics like AUC, or maybe more bespoke metrics like NDCG in search systems, can have massive impacts on business and social consequences. So this is why choosing a metric appropriately and understanding what it really measures and being really curious and skeptical about how it's computed in the first case is actually a big deal. I'm going to sound like really repetitive in this class because occasionally there's instances of the machine learning pipeline that seem like you don't need to worry about it. It's just one line of code from sklearn or some other library. But like if you don't think about it, then this can mean either your results are just not true and you've failed as a scientist and as a person, or you've missed an opportunity for like major impact in your organization, right? So all the more reason to just be very studious and careful. So on the other hand, again, like we're scientists, so we have to look at things from multiple sides. I just spent a bit of time talking about how differences in 0.005 can be extremely meaningful. But is it really meaningful, right? So we don't talk much about statistical significance in this class, but it'll come up occasionally. It might even come up a little bit in the following module when we talk a little bit more about how to set up experiments. These small differences can be meaningful in situations like I just mentioned, but also they can be the result of just accidental setups in your experimental scenario, and they may not actually be meaningful. In the next module, we're going to see instances where simply just changing the amount of data you're using for testing can change like your recall rates from like 40 or 50% to 7 to 8%, which is a massive difference, obviously, right? So differences of 0.005 can be meaningful. They might not be meaningful. We need to dig deeper. So here's kind of more like a suggestion. This is not really a cheat sheet, but it can be considered to be. First, make sure that you're doing if you're doing balanced classification. So if you have roughly equal numbers of positives and negatives, then start with accuracy. But then also it's very easy to compute precision and recall in F1. So it's better when you're reporting everything in your table of results to have multiple metrics and record them all. That way, someone skeptical like myself or like anyone you might work with might look at, they look at your accuracy, see that it's high, but they know there's all these traps that you can fall into that can result in high accuracy, but they can see precision and recall is also high and they'd be satisfied, or at least more satisfied. If there are rare positives, so in situations where like fraud or certain kinds of especially rare diseases, where the positive class is going to be in the deep minority, then you'd use precision recall curves, possibly a ROC curve. You'd downplay accuracy because, as we've seen multiple times, that's not very useful. We're going to see a bit later on like what kinds of other, like why it is the case that machine learning can fall into the trap of like misaligning when you have class imbalances like this. We're also going to see instances where you have more than just a binary case. So we're starting slow, but we'll see more complicated things a bit later. Yeah, if you're using ranking or recommendation systems, there's a whole other slew of metrics you might use. So like we talked about NDCG, for example. There's different measures of like precision at certain levels of recall. Like so, there's like levels of precision at different levels of recall. There's business-specific top K metrics. So like different tasks will have different bespoke sort of metrics that go along with it. When you're doing regression, this goes way back to the beginning. You can use MAE, you can use MSE, but each of these can, this depends on what you mean by robust. So maybe a bit of an asterisk should go here. And also one slide a bit earlier when I talked about how MAE might be more robust. It's more robust in the sense that it doesn't like overemphasize differences in the way that MSE does. When MSE, because we're dealing with quadratic differences and square differences, right? Like differences can be overemphasized for outliers. And if you only have a small number of outliers, this can sometimes result in like way different values for MSE compared to MAE. So MAE might be more robust in that sense. But occasionally hunting down outliers is what you want, right? And if you want the overall system to be robust, you might be more inclined to use MSE and to identify these massive differences so that if there's any bugs, they can be squashed. And again, like high stakes domains. So a high stake domain doesn't mean necessarily something that's being used for, national defense or in healthcare or even in, special deployments of finance. You have to consider costs always. So over and over again, I'm going to try to remind you that even in situations where we're dealing with like relatively simple cartoon scenarios of how many baristas to have on staff at a coffee shop, or whether or not you want to check a wind turbine for possible faults. Each of these have costs and risks associated with them, and those costs and risks are usually associated with false positives or false negatives, which now we have a bit more of a handle on. So you have to think about the real world costs. These aren't just numbers that we're dealing with hypothetically. They have real world consequences. So as responsible members of society, we need to remember that also. So I think I basically described this already. A model can get great metrics by exploiting confounds and other kinds of shortcuts to apparently fluff itself up and make itself look good when it's really not good. We want to try to avoid that. We want to avoid catastrophic failures on new populations or hospitals. We want to make sure that we're not amplifying any kind of existing biases that might exist in our data. We want to not give stakeholders a false sense of safety. So this is, there's two sides to this equation. This is more of a side note, but even today, there's a lot of kind of hype around machine learning. There's a bit more of skepticism on certain use cases of it, like you might have heard of some of these, but a lot of people who, like they see models getting great use, and they kind of assume that every use of AI is going to be perfectly performant. And that's obviously not the case. And the problem is sometimes if you're trying to sell AI to people, you might even with good intentions end up overhyping instances where you succeed and de-emphasizing instances when you do bad. And that's sort of an example of you using these metrics in a kind of a falsifiable way, like a false way. And then you end up misinforming people as to the true utility of your system. On the other hand, the flip side also ends up working. So like I've been on the flip side of this myself. Like I try to be very scientific and say, well, the results look pretty good in this particular data set, but then I have all these caveats. Like you've heard me complain about these things already. But then if the person receiving the model is kind of bullish and thinks, oh, this is going to work great, like, everything's going to be really performant, and they lack the kind of scientific mentality, then any kind of protestation you can have it's going to fall on deaf ears. They're not going to care about any warnings you have. They're going to deploy it, and then they're going to come back to you and say, hey, wait a second, you said your model was perfect. And, so my advice there is make sure that you're explaining any kind of reservations you have clearly, so even people like that can understand it. But also, as much as possible, get all of that and make sure you have everything in writing so that you're covered. Our responsibility as machine learning practitioners is to treat the metric choice itself as an ethical design decision. I'm not trying to be preachy here or anything, but you can see from even our examples how just simply choosing a metric or another can result in very different apparent performance. So this is, part of telling the truth, so it's an ethical decision. I want you to ask what patterns the model could be using to achieve this score, who is helped or harmed if this shortcut fails. I want you to connect evaluation to broader topics. We'll talk about some of these other things later on in the course, so maybe when you're reviewing these slides, you'll come back to this later, but always look at the big picture. As always, here are your quick checks. Please go to the slides and go through it yourself and try to uncover any challenges you might be having with this material. Thanks so much. Looking forward to Module 13.